Hello students, welcome back. We went through one example of Frobenius method. Here's another example. Yeah, we went through this one. And in this case, we had two different R values. We had 1/2 and -1, didn't we? 1/2 and -1. So when R is 1/2, you're gonna get one Frobenius series. And R is -1, we get another Frobenius series. So we have y1 and y2. We have two linearly independent solutions, so we get the linear combination of those, ay1 plus by2, and we have the general solution. Now let's consider where we have two different R values that differ by integer, or we have just same R value, so the difference is 0, again an integer. In that case, things will be a little bit different. Okay, here's an example. And by the way, does everybody recall this problem? This is something we studied earlier already. We studied it in Laplace transform method. But this time, let's just go ahead with Frobenius method. Okay, all right. Start from the Frobenius series and the derivative and the second derivative, the usual. All right, and then we're going to put those into the original equation. We don't have to break up anything. We just plug in y, y prime, y double prime. No problem there. Okay, and then let's work out this t times this minus 1, t times this minus 2 power, giving minus 1 power. And this t power times here, so we have plus 1 power. Now compare all these series, and these two have the same powers, and this one doesn't. So these two are okay, and this one will require some index shifting. The third one, I mean. Okay, let's apply some index shifting here. And well, I just gave you the answer here. All right, pretend you don't see it. Okay, here, from here. Okay, we want to get the same n plus r minus 1, so we need n minus 2 here, so that all these simplify into n plus r minus 1. So what did I just do? I replaced n by n minus 2. So that's what I'll have to do to all the other n's. And then consequently, this is what I'm going to get. I begin from n equals to 2, and then this whole thing becomes now minus 1 as we wanted, like this. And consequently, we get this last series from that index shifting. Okay? All right, let's remove it. Okay, now let's plug in n equals to 0, then we have only these two series, and this one does not contribute. Also, if I plug in n equals to 1, we get first two series, and the second series does not contribute. When n is greater than or equal to 2, in that case, we're going to get something. All right. So basically, that's what we have. Plug in n equals to 0. So n is 0, 0 plus r, and n is 0, so r minus 1. Here, n is 0, so just 0 plus r. So we get first equation here. And then simplify. Factor C0 out, factor, and we get this factorization. Okay? Factor r out, we have r minus 1 plus 2. So you get r is equal to 0 or r is equal to negative 1. So that's what we get from n equals to 0. Now what about n is equal to 1? You see, this begins from n equals to 2, so that doesn't kick in until n equals to 2. So I have to do these two again. Plug in n equals to 1. So plug in 1, plug in 1. This is what we get. And plug in 1, and that's what we get. Do the same thing, factor it out. We have r plus 1 common, so C1 r plus 1 common, and what's left is r plus 2. So the conclusion, C1 is 0, or R1 is negative 1, or R is negative 2. What conclusion do you get? Both of them have to be true, so we gotta have this. What about r equal to 0? Is that impossible? Well, in that case, r equal to 0 doesn't appear here, so C1 has to be 0, and that's going to lead to something special. And same goes over here. When r is negative 2, that's impossible, so C0 will have to be 0, and that 2 will lead to something special. But you don't really have to consider something special unless this one fall into brick wall. If you do get something from r equals to negative 1, that's about it, because you see, we have the existence theorem and uniqueness theorem, the fundamental theorem. So no matter what method we use, if it works, then it works. We have the unique solution. So all you have to do is to find out those two linearly independent solutions, y1 and y2. And if you get both of them from r equals to negative 1, that's it. If you don't, if you have just one, then I have to come back and consider r equal to 0, and consequently C1 is equal to 0, or r equals to negative 2, and consequently C0 equal to 0. We have to consider it then, but that can wait. For the time being, let's focus upon r equals to negative 1 case. Alright, now when n is greater than or equal to 2, then all three series will contribute, and you're going to get this recursion. As usual, I discarded t to the whatever power because that's the same anyway, so they're going to be all cancelled out. Let's consider all the coefficients only. So from here, I can solve for Cn. And solve for Cn. A bit tedious computation, so I'll just scroll. And then we get that. Oh boy. If you actually have to do this by paper and pencil computation, it's going to take a while to get that. I just wanted to save time, so I just scroll down. But it's not a simple computation to do. Elementary, yes, but not simple. Okay, we have this general recursion, and then we have to consider r equals to negative 1. That one first, before anything. And if that fails, maybe we can consider some other cases. Okay, r equals a negative 1 case. Ready, everybody? Okay, let's go, open it up. Plug in r equals a negative 1. We get, well, let's see, negative 1 plus 1, so that's 0. So we have just n plus r. And then no, actually, no. Excuse me, I just copied it. Just change the order. And then I'm about to plug in r equals a negative 1 here. Okay, all right. And then C2 can be calculated from C0 by plugging r equals a negative 1 here, which I did here and there, and then we ended up with this. A curious way to calculate this, something simple. I mean, why don't I just plug in r equals to -1 here? And then plugging in r equals to -1, then I'm going to get just n. Yeah, we get that. N times n minus 1. Okay, we get to this one directly. So I can bypass this part and go to this directly. Next, C4 will be 4 times 3 times C2. We'll get to this directly. But then again, C2 is what we had before. So we get that. And that's C6. And 6 times 5 times C4. No, I'll take an extra step. Times C4. And I forgot the negative sign. All right. So we can find out the pattern here. All the evens are there. And the denominator is factorials for the even numbers. And we have alternating sign, -1 to the k power. Haven't you seen this before? It's deceptively similar to something. Alternating power, and then even number factorial. How about odd number case? It's the same deal, but C3 will be determined by C1 and so on. So yeah, plug in 3 here, and 3 times 2, and then C5 will be determined by C3, so we get that, and C7, so that will be 7 times 6, and then that's okay, all right. So we have factorials of the odd numbers and an alternating sign. Again, haven't you seen these coefficients before? Putting together, we have this. So r is -1, so -1 power, and this, even factorial alternating sign, and then odd factorial alternating sign. These are cosine and sines. And then t to the -1 power, that's common. In the end, this is what we get. A linear combination of these two functions, cosine of t over t and sine of t over t. So, by considering that same r value, r equals to -1, I got actually 2 linearly independent solutions. One Frobenius series that consists of even terms, and another Frobenius series that consists of odd terms. And I put those together, turns out to be cosine of t over t plus sine of t over t, like that. Again, this is one of the rare simple case that you can actually find the pattern. Most of the time, you don't see the pattern. You just put switch several numbers and put ... and that's about it. Now, the other cases are unnecessary, but just for instructional purpose, let me just show you. And what if no, not this case. What if I consider r equals to 0 case? You see, this case. And then r equals to -2 case. When r is equal to 0, then it doesn't satisfy any of these, so C1 has to be 0. And R is negative 2, then C0 has to be 0. So when R is equal to 0, what am I going to get? Plugging into the same recursion, we get that. And then for all the odd numbers, C1, C3, C5, they're all zeros. C1 is equal to 0, so all zeros. Not surprising because we are starting from 0. How about C0? From C0, we do the same thing. Then you're going to get all the odd factorials. And the same thing you got before. And we end up with sin of t over t, the same thing we saw before. If you go to green, then, well, it's not really necessary, but if you actually do it anyway, then you're going to get all the odd factorials come alive, and you're going to get, all the even factorials come alive, so we get cosine of t over t like that. But as I said, those are unnecessary because they are already covered by this r equals -1 case, which are common here and there. And that is generally the case. For some really rotten luck, if this common r value does not give you all the solutions, then you may have to consider these exceptional cases. But those are rare. In any case, that's the kind of situation you're going to get if you have just one r value, or the difference is 0, or two r values but difference is by integer. So even though we have two different Frobenius series, but they overlap and end up being the same thing, and we have to consider something else. That something else is going to be considered in the next example, and that's something we're going to discuss in next video. Okay, let's stop here.